that's Daniela. So I have to tell a story about her too, because I told a story. So she's from Beirut, and she's taking care of refugees, and that's why she's not here. Yeah, no, it's true. It's true. Right. So this is a really important point. Like, if you want to take anything from this second little talk, then it's what I'm going to say now. So what I gave you earlier was an algorithm for vectorial meaning composition. I described how you do that. But if you look at this paper and you look at it carefully, our first paper, you know that this is actually what we did. We gave an algorithm for X meaning composition, where X can be pretty much anything. So the only thing you need to have in your X is the ability to interpret such a diagram as something. That's all you need. So you need, to say this in other words, you need to be able, you should have spaces in which you describe meanings which can be organized as a compact closed category. And that's pretty easy, because the standard constructions for that. So, of course, what are the interesting examples of things you could do instead of vector spaces? I mean, if you take Boolean matrices instead of matrices in real numbers, you exactly get Montague semantics. This exactly gives you Montague semantics. So that's a nice example. So it means all the Montague stuff was actually an instance of what I was just talking to you about. Now, an unfortunate thing is that Montague semantic is beautiful, it's logic, it's essentially logic. Now, whenever you substitute your Boolean matrix with anything non-Boolean, your logic is totally gone. So, one thing I actually was saying, yeah, we want to have words like and not and things like that having logical meanings, but it actually doesn't work. Because, for example, there is only a not in 2 dimensions. The only linear map not that exists is one in 2 dimensions. So which puts you automatically in this case anyway. And, I mean, Dimitri is going to talk about and, so we have ways to deal with and. Hey, you're right, we're going to talk about and later. Yes. So that we managed to get ways to deal with these things, but fundamentally, vector spaces hate logic. Hate logic. It doesn't work. It doesn't work. So we came up with another idea. We said, okay, let's use density matrices. I don't know whether you know what density matrices are, but it's something von Neumann introduced in the start of quantum mechanics. And density matrices were introduced to express that you have a lack of knowledge about the precise state of your quantum system. So it's a probability distribution over your possible states. And this gives you a different mathematical object. And, I mean, this turned out to be really useful because actually how it worked was I had this idea. I had this idea many years ago. I said, we can use density matrices to do lexical entailment, and I told to Dimitri and to Robin, yeah, you have to do this. Dimitri was doing his PhD, Robin was doing his master, but actually they're a lot smarter than me, and they came up with something much nicer. So they use actually density matrices to encode ambiguity. It's just plainly obvious if you got a word like queen, which is ambiguous, which can be any of these 4, then you just build the density matrix of the 4, because you got a lack of knowledge about what your actual meaning is. It's so canonical, it's so natural, it's weird that nobody came up with it, as far as I know. So I mean, these two guys are not physicists. I told them this is a density matrix, they went away and they came up with that use. Right, am I right? So, okay, then we use density matrices for something completely different, which is lexical entailment. That's actually what I always had in mind, that we should use density matrices for. And lexical entailment is this sort of. A tiger is a big cat is a mammal. That's lexical entailment. That you got some sort of implication order between words. It's easy, it's obvious that you can't do that sort of stuff in vector spaces. There's no natural, I mean, you have normalized vectors, they all are on the same footing. It's not one vector includes another vector. I mean,
why not inclusion of the supports of the inclusion of the supports of the probability distributions of the vectors? And that's what people use.
Is that, yeah, but that's very crude. That's extremely crude. Inclusion of support. That's very crude. That's not probabilistic.
There was an interesting PhD thesis a few years ago by
Oh yeah, I know. Yeah, I know it.
So
yeah, I know
it
it.
developed to.
Yeah.
I don't know where it's gone since, but it's.
But he's not in academics anymore, even. I think.
Oh wow, okay.
I like you.
Maybe even a more sophisticated version of this is something like, Jensen divergence or Kale divergence. So they are trying to do it in a probabilistic way.
Okay. Yeah. Yeah. I mean the core. It doesn't really matter because the core to doing something like I was just trying to say, doing lexical entailment, is that you want to partially order your density matrices, which you can do, which is non-trivial. But the key to actually ordering your density matrices is actually ordering your probability distributions. As a mathematical problem, it all boils down to ordering your. And the next talk is right. It's going to be exactly about that. Like how many ways can you order probability distributions? Because that's what you need to do. It's a totally non-trivial problem, ordering problem. So if you look at probability, as an exercise, you should try this. You take all probability distributions on 3 elements and come up with a partial order such that, you get like the endpoints of your triangle minimal, the maximal, some sense of continuity. Just try to do it. It's extremely hard. And it's hard now, you know why? Because there's actually very few solutions. It's
well, not very few. It's like order n squared, different parameters you can choose.
That's nothing. That's nothing. That's nothing. Now am I doing with time? Okay. Oh, that's good. Right. So once you do that, so once you order these density matrices or probability distributions, I don't know, then actually you get some notion of conjunction and disjunction because you power laws and some kind of negation, which is the sort of thing you did. It sort of falls out. So you did quantum logic. Quantum logic embeds in here, but you got a lot more. So you have to think of quantum logic as sort of Boolean propositions, and then these density matrices is sort of the probability theory, the probabilities over Boolean propositions. So you got a lot more stuff here. That's where you go way beyond something like support. You really have probabilistic data, and that's what makes it hard to actually order these things. But you can do it. You can do it. Now, I was just looking through a list of things here, and then in October, Marta said, "Oh, I'm going to Berlin." And I said, "Oh, I go to Berlin too." And I didn't know. I said, "There's some people there. And who are these people?" I don't know. I just want to go to Berlin.
I didn't say that.
and then I met those people. Then I met those people, and then we got excited and we started the reading group on conceptual space, and we'll hear later today what came out of that. So, but this is like going way beyond anything that's even has to do with vector spaces and still do this compositional reasoning. So we know how to do this now. So just to make my list, there are many possibilities of different types of spaces you want to work with. And one idea which I have, Peter, is that we should actually have spaces which are directly based on physical space. Euclidean, because you like that.
I like that.
Yeah. So we're going to do that.
We have some things to do in the afternoon, yes.
Okay. Right. Now, here is the thing. Here is the question, and this is sort of still in the same thing. Now, suppose you want to both talk about ambiguity and lexical entailment in one sentence. You've got a word which both involves ambiguity and has some lexical entailment with other words, and you want to encode all of that in your model. How are you going to do that? Because we can do this with density matrices, we can do this with density matrices. You can only use them for one thing at the same time. And then, then the brilliant thing is that we are working categorical, so we can do categorical constructions, and this is how you do it. It's a simple trick, and it's an amazing thing which I think that physicists never use that sort of stuff. So this is density operator formally. You got some probability distribution, you got some vectors, you build this cat brown, which is an operator. This is an operator. This is like you build it, and then you just mix these operators. That's how you build a density matrix. That's how you do it. Now, people have been doing it wrong for like 100 years now, because this is how you should do it. This is how you should do it. So instead of taking a cat and a bra and make an operator, you should actually just tensor these two things and make a vector in the tensor space. I mean, it's totally, it's an equivalent representation to this, but it's just much better. Why? Huh? Oh, conjugate. Yeah, you have to conjugate. What?
Is this not real?
It doesn't matter, but I mean,
If it's real, it's just.
if it's real, it's nothing. But I mean, if it's complex numbers, you have to do the conjugate. Otherwise, you don't get anything equivalent. So basically, what this operation boils down to, I mean, yeah, I can write it down there, is that if this is your density operator, then you do what I showed, then you just bend up a letter, and it becomes a vector. That's what you're doing. Now, why is this a good thing to do? It's because you can do it again. You can now take two of these, think of them as vectors, and build another sort of density matrix level on top of that. Now, now intuitively, what people then think is, I mean, you take stuff, you mix it more, but then you're still just with a mixed thing. No, this is totally different beast. Because this is totally different beast. It looks like this now. You got like 4 things instead of 2 things. Okay, that's interesting. What can we do with that? This beast is a density matrix or density vector in 2 different ways. So you can write this in 2 different ways. Here it's a density vector, and here it's another density matrix. So it's sort of, that's why we call it dual density matrix. So it's a density matrix in 2 different ways. And what's really interesting about it is that it admits 2 spectra, not 1. It has 2 entropies. It has 2 notions of purity. It can be pure along one line and not along the other, and vice versa. So it has these 2 independent dimensions of being a density matrix. Have you ever seen it?
I mean, you know, this are called purifications.
Huh?
These are called purifications of a density matrix.
No, it's very different. It's very different. It's very different. I mean, you purify a density matrix. What?
Go to a larger Hilbert space, so if you trace over it, you get the density matrix back.
Yeah, but that's not this. Then you get a pure vector. No.
Well, in the first step it is.
Okay. No. So, anyway, for one of each of these, you get the notion of this sort of stuff. I mean, what are you doing in diagrams? Because we like diagrams. So this is the usual representation of a CP mapping diagram. Completely positive map. Peter Selinger came up with this construction. That's how a general completely positive map looks. So this is how a dual completely positive map looks. So you see there's a lot more wiring going on. So basically you got this wire is the same as this wire, and this wire is the same as this wire. So if this wire wouldn't be there, you have purity in one sense. Okay, if this wire is not there, you got purity in another sense. So this is how the dual density matrix state. Okay, I have to go. So how do you do Beirut? Now we're going to do Beirut. So I mean, I have no clue. That's Daniela came up with this example. But let's write Beirut city as this density matrix, which means it's the sum of some area and some other area. So you really think of the area as entailing the city. You know, it's not serious, but and then I mean this is embarrassing because it's a horrible band. So this band is made up of a guy called Paul and a guy called Zach, and it's called Beirut. So you make this density matrix, and now we want to write down what. So this you have to think of as exploiting the idea of lexical entailment. You know, like this is the more general, and these are the individuals, like Tiger, and now we want to actually say that Beirut is ambiguous and can have 2 meanings. It can be a band and it can be a city. So what we do now is we do exactly the same. We double these guys up, and now we're living in this dual density matrix land. And so so you get actually the meaning of the city of Beirut. And then, I mean, then you can start computing. I'm not going to go this because I ran out of time. But we have a way to encode that using these spiders, both as an object or subject relative pronoun. And then you can ask the question, Beirut that plays at Beirut. Or you can ask the question, Beirut that Beirut plays at. And you want to get 2 different answers. If it works, I mean, you can check the competition, and if you do Beirut that plays at Beirut, you get Beirut band, and if you do Beirut that Beirut plays at, you get Beirut city. So it works. It works. Anyway, that's the sort of thing, of course. Yeah.
But you do get these things in the vector model as well.
What?
You do get this in the vector model as well.
No, but how are you going to encode this thing? How are you going to encode this thing? You both need entailment and ambiguity to be represented independently.
Well, in the early days of distribution semantics, a guy called Schutz came up with a way of having two different meanings for each word and two different vectors that have represented two different meanings.
But so what you say, you used vectors for ambiguity. Yeah, this is like working on the diagonal of the density matrix, because there you get your probability distribution.
So what do you get more here?
You get a big what?
What do you get more here?
What you get more is you get two notions of summing. You got one notion of summing which generates ambiguity, and you got one notion of summing which generates lexical entailment. So the more general out of the specific. So they have two different things. Now one could philosophically argue that they're actually not that independent. I can buy that. Okay. But, more than anything, it's just an illustration that you got a problem, you change your model. Whether it's the right solution or not doesn't matter. But okay, density matrices were not enough. You go to dual density matrices. You want to have something more, you can do this again. And you can go on and go on and go on to infinite whatever density matrices. But then you need like post-quantum computers to deal with that or something like that. And we have to change physics first to actually be able to deal with that, I think. But, yeah. Okay, that's it. Yeah.
To what extent are these models of meaning empirically validated? For example, with respect to human judgments of entailment.
So Dimitri definitely did some stuff with ambiguity.
Yeah.
Because you're still working essentially in an ambient vector space. So a lot of the stuff, clustering or something like that.
Yes. What you can do is you can define carefully your pure states, which will be, let's say, vectors generated by a word sense disambiguation system, and then have a way to define your density matrices to mix these pure states into mixed states density matrices, and then let the quantum measurement actually to do the job by composing this. It's a bit, yeah.
So what I meant was that if you take human data about sentence entailment and judgments of meaning and judgments of synonymy and all these kinds of things, presume your models make various predictions about those kind of relations. And my question is a question about to what extent your models agree with human.
Yeah, I think that's this sort of stuff.
Yeah. So this is sorry.
Actually, building this density matrices is extremely costly because already we have tensors. And then if instead of a vector you have a density matrix, you have a tensor for words as well. Whereas previously it was just vectors for words and tensors for verbs. Now you have tensors for words and double tensors for verbs. It's difficult, very costly to build these density matrices. As a result, you haven't been able to get good models, good numbers like these. You haven't been able to get them for density.
If you got a quantum computer and a density matrix, density matrix is equally cheap as a vector. Because it comes automatically.
We have some toy examples, in a small corpus of 20 instances or something like that. But we need a large scale evaluation. We don't have that.
Okay, thanks.
So, the question of ambiguity, well, many words are ambiguous all the way down, right?
Sure.
The idea of
Yeah.
districts of Beirut can be decomposed and decomposed. So how do you actually choose the individuals given your corpus?
There are algorithms called word sense learning.
Yeah.
And you can look in the dictionary.
Basically, these are based on clustering. Imagine you have a large corpus, you cluster your words, and then you cluster the context of the words. And then you see, for example, bank. The word bank should have created at least two clusters. One related with context related to the financial sense, and one with context of the river sense, for example. And then you can use this in order to build your vectors to represent senses, your pure states, let's say.
Yeah.
Hans, I wonder.
I have a question related to the second short talk that you gave on really quantum implementation, exploiting Grover type things.
Yeah.
And you emphasize that, yeah, in fact, we need very small number of qubits only. What's not clear to me, and this is also relates to my comments on the existing quantum machine learning algorithm.
Yeah.
What you know, if you want to use that, you want to have a meaning process, or somehow you have your dictionary, and that using these quantum tricks you first have to construct a database.
Sure.
That is stored in a superposition type of thing for this thing, which, okay, suppose you have it, then you can do your task fast.
Yeah.
But the drawback will be, having done it, you will have to reconstruct the database to do the next task. And now the question is, you know, the constructional effort in constructing the database will probably you know, this Grover advantage is probably
that's like you said, it's this quantum machine learning stuff is all pretty controversial.
I think there are clear statements there, but the assumption is that you do have a quantum RAM, or in this case,
you need QRAM, or
and
something.
this has to be reconstructible.
Yeah.
That is.
I mean, but who are you to? I mean, I'm doing this with guys building quantum computers. He really builds them. Well, that's what he tells me.
Sometimes the ambiguity in the word is not simply the ambiguity between two interpretations of the word as nouns. One word can mean a noun in one interpretation. It could mean something of a different type, say a verb.
Yeah.
Bank, for example.
Sure.
You can bank on it.
But that's a problem which already starts at the parsing level, I guess. Just trying to figure out what your grammatical
I was
structure
just
is.
wondering how this sort of, double density
When-
makes
So,
sense.
a simple thing you can do is when you create your vector space, to do this distinction at that stage. So basically you have a parser, or a post-tagger is the correct term, that gives you the types of the words. So by examining the context, the tagger can tell you that bang here is a verb, or bang here is a noun, for example. And then you build a different vector for each type.
I understand that, but Bob's scheme is a little different, so it seems to me.
Just to kind of add to that, what would be really challenging and a big benefit for natural language processing from this is, yeah, we can disambiguate part speech disambiguation of bang, but that would leave, if you do that first, that leaves you with the problem of figuring out two completely different meanings, one for the verb, one for the noun. And of course, the reason that people like verb nouns is precisely because we're too lazy to learn another word. It's fine for us to just use the same word and we know what it means.
Yeah.
No, actually, that's a sort of positive challenge. I think you might be able to deal with that in this sort of framework in ways that you couldn't in others.
Yeah, and one thing one should realize is that these vector space models, the meanings, you shouldn't treat this as something exact or really or good in any way as a model of meaning. You know, it's pretty crap as a model of meaning, because typically opposites get the same vectors because they appear in the same context. For example, I mean, there's ways to fix that, but for me, all of this is what is meaning and what is a good model of meaning. And then there are the two aspects. Do you want to use it in NLP, or do you just want to be an academic and think about it? I mean, it's a little bit, for me it's enough to think about it, but then for people like Dimitri, they need to get jobs. So that's a bit different.
What is the connection between what Hans has a speed of and your speed of?
Oh, but I mean, it's all quantum computing speed up.
Why are they different? Because that was quadratic.
It's different. There's different problems. I mean, means like shore has a very different speed up than groove.
So it's shore versus groover.
No, this is all more grooverish, I think.
Yeah.
This is all more grooverish. But each problem has a different sort of.
I'm not sure whether it's relevant, but if you ask the question, in the application I was referring to doesn't need to store quantum states. The memory is not the quantum states. These are hopping probabilities like control parameters from the outside. One person will excite quantum states dynamically. So it's not, you don't need to have a coherent superposition of the database.
So the clips are not quantum, but the links between them.
The links are like interactions with hemoglobin, and the clips are excitations that come in, you excite, and you propagate, and then you de-excite.
So the only the main insightful thing that I forgot to say here is that you actually never compute the meaning of the sentence. That's the way our quantum algorithms work. They don't compute every possibility. There's some sort of thing people tell you, but that's actually not how it happens. It's actually there is some sort of sub-problem, which here is the distance to this thing, and it will give you the solution without actually really computing the meaning of the sentence. And that's how that's sort of how every quantum algorithm pretty much works. So that's sort of the cool upshot here. So you never need to deal with sentence space basically.
Okay, last question.
So you've got a really interesting way to represent ambiguity, but in real natural language, ambiguity gets resolved. So, you know, in a conversation, you may figure out what word meaning somebody really intended.
Yeah.
So, do you have a story about
That's exactly
resolved?
what I showed here. That's what's happening here.
Mm-hmm.
That's what's happening here.
So you can think that
So you stick in the meaning here Beirut, and here Beirut, and here Beirut is the sort of very ambiguous Beirut.
Right.
But
that's
if you then compute this,
Yeah.
if you compute this sentence, like basically this is like computing this diagram, you actually have resolved the ambiguity by the way these two words fit in
But
the sentence.
sometimes ambiguity is resolved in a sentence that comes later in a conversation.
So yeah, okay, so okay,
So
no,
it's
this
not
is
within
just,
a sentence.
here it all has to happen within one sentence.
Yeah. So do you have? You don't
So
have, yeah.
I have been thinking actually that probably text could be also modeled with these wires, because usually one sentence refers to bits of other sentences, and maybe we could use exactly the same formalism to sort of model text and then things like that, but
Okay.
we haven't gone there yet.
Great.
But
okay, let's thank Bob.